It works? Yeah. Okay, yeah. So thank you very much for your invitation and for an opportunity to give a talk here at this nice workshop. So I need to apologize first. Probably it will be the least federated talk of today, but it will be rather on some more fundamental aspects of optimization with Markovian noise. Which yet covers some interesting specifics, which also arises in decentralized optimization, in different privacy techniques, and also in the federated learning. So my today talk will be based on our joint work with Alexander Beznosikov, with Eric Moulinet, and with other team members from our Russian HSC team, with Alexander Gasnikov, with Alexei Naumov, and with Marina Sheshukova. So this paper is accepted to the CNU RIPS. So the general problem that I will be talking about, so okay, it is a standard minimization problem. We have some function f of x, which is an expectation of some oracle function large f. You don't have access to large f. You don't have access to the gradients. You don't have access to the function small f itself. You have access only to large f and to its gradients. And contrary to the ID setting, we don't assume that the noise variables are sampled independently, so it is time homogeneous Markov chains. And there are quite a lot of examples where this type of problem appears. So you can assume, for example, the kind of token algorithms. You can think about Markov chain SGD or its differentially private versions with additional additive noise in the gradient. And in general, you can think about the setting of decentralized optimization as maybe the routine of primary interest for this type of results. So the main ideas that we will talk about are the following. So we provide kind of uniform framework which allows to cover both the setting of strongly convex optimization problems, non-convex problems, and monotone and strongly monotone variational inequalities, based on a simple idea of using randomized batch size. So apparently this idea falls nicely into all mentioned frameworks and allows to obtain theoretically optimal results, at least in the worst case, optimal. So we will put some standard technical assumptions. So the problem is L smooth, mu strongly convex, at least for the very beginning. And from our noise variables, we will assume that the sequence of noise variables Zi forms the time homogeneous Markov chain, which we will assume to be uniformly geometrically ergodic. And moreover, we will need to impose some additional condition A4, which is also quite classical in the optimization literature, but typically when you speak about independent noise setting, it resembles the strong growth condition, and it allows us to somehow control the noise which comes from the gradient oracles. And the general idea that we will present, so I will not get too much into the technical details presented here, but the main idea of all the three frameworks, which allows to obtain tight, theoretically optimal guarantees, will be to use the batch size, which scales actually with a sample from a truncated geometric distribution, which is appropriately rescaled by additional parameter which corresponds to the batch size large B. Apparently, this parameter large B will be of primary importance. You can think about this scheme as somehow about something which is also inspired by a multi-level Monte Carlo, because you see that when you account for the stochastic estimate of the gradient, in this case, you use the previous sample estimate as kind of control variate, which allows you to have a kind of nice telescopic property of the estimate. You will show that this technique is extremely useful to dramatically decrease the bias of the stochastic estimate, and at the same time to have only quite moderate payment in the variance, apparently. Because of course, when you work with Markovian type of optimization, and if you run the recurrence, you start to count the k+1 step error in terms of k step error, and apparently when you take a conditional mathematical expectation, you will no longer have unbiasedness property of your gradient oracles, contrary to what you have in the IAD setting. And that is the main challenge, and this bias can be exactly reduced by the proposed randomized technique. In the non-convex setting, it appeared previously in the ICML submission 2022 by Dorfman and Levy, and here we somehow generalized it. What is the main feature of this technical idea, if you wish? You see that if you scale the maximum batch size with a constant which is large M, you can decrease the bias quadratically with this parameter M, and at the same time you pay only logarithmic factor of this parameter M for the associated increase in variance, which is a very nice trade-off and allows you to balance the two sources of error somehow. Then we can have some results on the sample complexity of the, first of all, of the optimization problem with strongly convex constraints. And if you consider the strongly convex setting, our sample complexity bound that we proved with this randomization technique, it matches the results which are known for the case of independent noise setting up to the multiplicative factor of the mixing time. So basically, it is exactly what you should expect for when you start to do optimization with the Markovian noise. And apparently, we will show that you, in general, you cannot do better until you put some specific assumptions, some more specific assumptions on the problem. And this phenomena is already known because, for example, if you deal with regression with Markovian data, then you have very simple algorithm, which is SGD with data drop, which can be shown to be optimal for this setting. And apparently, you cannot do much better than just skipping every, than just taking every tmix iteration of your chain, then proceeding with some update, and then continuing iterates. And basically, our results shows exactly this. At the same time, it is the first analysis of the strongly convex optimization problem with the Markovian noise, which allows for both the optimization and noise terms, which scales linearly with the mixing time. So before there was a gap in the literature in this direction. And we can show that our result is apparently tight. So basically, we can show that the presence of the mixing time is not an artifact of the proof, first of all, neither in the variance part nor in the optimization part of the noise. And the only thing which is maybe not tight in the previous analysis is the dependence of our sample complexity bound on the constant delta squared, which comes from the strong growth condition. It is also not an artifact of the proof. We can provide a respective example, but nevertheless, the dependence on this condition number perhaps could be improved in the upper bound. So here it is just a table to show that exactly our result matches the sample complexity for accelerated SGD up to this additional multiplicative factor of mixing time. In fact, so I will just skip this slide. In fact, if you switch now to just convex minimization problems, then you can come up with a simpler version of the algorithm just for a randomized gradient descent, which allows for the same randomization scheme. Now, previously, the algorithm that we considered was a modification of Nesterov accelerated gradient. Now it is just simple SGD with randomized batch size. And apparently, if you apply it to L-smooth problems, so either convex or even not convex, so you completely remove A2, you can show that the resulting algorithm is minimax optimal. And again, it has exactly the same sample complexity as the one which is the one which corresponds to the independent noise setting up to additional mixing time factor. And again, so the corresponding bound for IID setting was of course already known. And moreover, what is also nice about the proposed technique is that you can do exactly the same. So you can trace the same stochastic gradient estimates for the stochastic extra gradient algorithm, which is kind of natural and optimal counterpart of either accelerated gradient descent or just gradient descent for the case of variational inequalities. And if you switch to the example of VI, if you switch to the example of VI, then basically you can think about them as a kind of minimax problem with approximate convex-concave function G and a couple of convex functions R1 and R2. You can show that basically having these same assumptions, which duplicate the L-smooth and strongly convexity assumptions from the minimization part of the talk, you can have, okay, I will show the results only for the monotone VIs in this case, achieved with the randomized extra gradient scheme. Introducing the standard gap function as a measure of the performance of the algorithm, we can show that we have a sample complexity, again, which is linear in mixing time, which is the first result of this type in literature. And moreover, we can show that, again, it matches the results which are presented in the IID setting up to these additional mixing time factors. Similarly to what was presented before in the optimization part, you cannot do better unless you put some specific additional theoretical assumptions. And of course, there are further directions about how to generalize and how to apply this randomized batch size methodology in different examples. And here, first of all, I will tell about possible generalization, which are related to the dependence on the mixing time, because all this theoretical optimality requires that we know mixing time in advance, which is of course a problem. And in the decentralized setting, for example, it's quite hard to estimate a heating time, which corresponds to the, for example, communication matrix of a graph. And at the same time, it will be nice to consider applications of this randomized technique, which is shown to be theoretically optimal, to the federated RL setting. We are working on this with Eric. First of all, starting from the policy evaluation problem, especially for the case where we have a couple of agents who are trying to evaluate a single policy. And probably these agents could act with the additional environmental heterogeneity assumption. So perhaps they could receive different rewards from the environment. So basically, this paper is accepted to new RIPS, so it's available in the archive. So if you have any questions, please.
Yeah, nice talk. Thanks. One question, I saw the algorithm quite, I'm not sure whether you know that the literature, that paper, I think Li Hua and Mike, I think a few years ago, they have this controlled like variance reduction SCSG algorithm. I think from the algorithm side, it looks pretty similar. Would you like to comment on like the connections or like the improvements over that particular algorithm?
Yes, it's a good question. So first of all, here this randomized batch size, it first of all allows you to reduce the bias, which comes in the which is the inherent problem in the Markovian setting. But yeah, for the control of variance, somehow it is hidden beyond this two-level structure that comes from the subtracting like the slower size estimate. Yeah. So yeah. Somehow there are some connections, so you can think about this subtraction as a kind of very specific control variate.
Thank you for the talk. I have a technical question about the assumption of this almost sure bound on the stochastic gradients.
Yeah, so I think I can guess what is the question. Yeah,
yeah.
Of course, it can be strong, but it comes from the fact that we use total variation. We use Markov kernels, which are geometrically ergodic in the sense of total variation, first of all, due to technical reasons. If you want to consider unbounded setting, you need to go beyond the total variation mixing, and you need to consider, for example, weighted Wasserstein metric or something like this. It is possible. So there are results which allows, for example, to do even the p-moment analysis for this setting. But it becomes much more involved technically.
Is it sufficient to assume the same, for example, but with some probability, with high probability that will depend on the batch size, like if you estimate gradient?
It's a good question. I think that potentially yes, but then yeah, you need to be I think careful when you will do kind of union-bound document in this case. Yeah, but I think that it is probably doable, but maybe more probabilistic viewpoint, a more probabilistic solution would be just to consider another types of mixing, which are, for example, which will allow you to control, for example, the functions which are Lipschitz and not only bounded and something like this.
Okay, thank you. And maybe a comment on dependence on delta squared. You say that it's unclear, is it tight or not?
It is clear that it should be present, but it is unclear if it is tight or not in our current bound. Yeah.
I think since it's related and covers zero-order methods, which is delta squared in that case will be proportional to dimension, and this should appear in the upper bound, like it should be proportional to dimension due to Nemirovsky and Yudin lower bounds. So I think this argument should hold. So you can just, as a special case, because it's very general noise setup, you don't need, I think, to, you can just reduce this to known setup. So, I mean, to the special case. Yeah.
Okay, thank you.
Thanks, Sergei.